In my recent research, I've generalized Feynman's path integral formulation of quantum mechanics to the case of a complex-valued time discretization index. In Feynman's classic textbook, Quantum Mechanics and Path Integrals, he lays out a particular procedure for calculating the probability amplitude that a particle will arrive at a particular location in space-time. His work is a very well-known reference work in the field of particle physics, quantum field theory, particle phenomenology, and the process of calculating a path integral by the process of time slicing is very well known. What I attempted to do was to generalize this procedure of time slicing, whereby an integral of all paths that a particle can take between two different locations in space-time is computed by dividing the time interval into a number of sections and computing a multiple integral over that many discrete time sections and then taking a limit, to the case of a complex valued time slicing index. In the time slicing approach, the path integral is given as a limit of a multiple integral as the time slicing index approaches infinity. If the time slicing index is allowed to be a complex number, as I showed in my paper, then this path integral adopts a spectrum of different results. Following in the footsteps of previous research, especially Steven Weinberg's groundbreaking 1987 paper, which analyzed a generalization of Einstein's field equations to the case of a cosmological constant and associating each different cosmological constant with a different universe, I took the spectrum of results that came out of this limit of a complex valued time slicing index. It yields a spectrum of different results because of the number of different ways that the index can approach infinity in the complex plane. And each result I associated with a different universe. This may seem like a strange idea, but in this particular field of research, it's actually a common one. Not only was there Weinberg's paper, but in the field of superstring theory, there was an approach, very well known and controversial approach, called the landscape approach, whereby different Calabi-Yau manifolds, which specialize the structure of space-time within superstring theory, apply to different universes. So different universes have different mathematical shapes for these Calabi-Yau manifolds, and thereby have different, essentially different physical properties, different laws of physics. Following in their footsteps, I generalized the Feynman limit for the path integral to the case of a complex valued time slicing index. May seem like a strange idea, but really I looked at it in a mathematical way, and the actual equations are consistent, and allowed each different result obtained to apply to a different universe, different physical reality. Now, I made several different assumptions in my particular generalization. In the analytic continuation from the standard Feynman limit to a limit of a complex valued time slicing index, I maintained the status of the contribution formula. That's the path integrand that each path makes to the overall functional integral as a phase factor. Now, in Feynman's original approach, the status of the path integrand as a phase factor, that is, that two different paths differ only in the phase of their contribution, not in the magnitude of their contribution, was a fundamental tenet. And to maintain this generalization as natural as possible, I maintained the status of the path integrand as a phase factor. I did this essentially by introducing a real part into the exponent that defines the phase factor, that is, taking the real part of the action in the contribution formula for the phase factor. This way, the fundamental property of the path contribution as a phase factor is maintained. And thus, this yields the most natural analytic continuation possible. And so, in the desire to generalize Feynman's equations and thereby produce a spectrum of possible results that apply to different universes, I maintained the fundamental properties of the path contribution. Now you might wonder, what is the point of all this? What is the point of this particular generalization? Now, following in the footsteps, as I've said before, of previous researchers, it seems clear that there is a distinct possibility that each of these different, essentially, results, each of these different laws of physics obtained by generalizing Feynman's limit could apply to different universes in an expansive multiverse. This is obviously a controversial idea. This is obviously an idea that's been debated before in the context of string theory. And by applying it to Feynman's path integral formula, I've created a new and unique way about looking at multiverse theory. This could pose potential applications, perhaps in fields as diverse as electronics, antimatter production, space travel, if these different universes exist, which is very unlikely, but I suppose possible given the naturalness of this mathematical generalization and the consistency of these equations. If these different universes exist, and they could be utilized because of the lack of conservation of energy and matter that apply to these different physical laws, due, as I explained in my paper, to the lack of a unitary nature of the probability amplitudes in these different universes, antimatter, for example, could actually be generated through using these different universes. It's a very, very far-fetched idea and probably won't turn out to be the case, but if it could be used, that would be a revolution in antimatter production, electronics, perhaps military applications. So really, this idea could connect well to other theories in the field, as well as offer perhaps some potential applications. Thank you.